Today we're looking at recognizing and applying the logarithmic laws. And specifically we're hoping to solve logarithmic equations. Now, before we can understand this, we probably first have to know the index laws. And these I think we know quite well. For instance, if I have a look here, taking something like 2 to the power of 4 times 2 to the power of 2, we would simply add the powers, and that would be equal to 2 to the power of 6. Likewise, if I was to take 2 to the power of 4 and divide by 2 to the power of 3, we would subtract the powers. We'd end up with 2 to the power of 1. If I look at raising one thing to the power, and I might alter this law a little bit, let's say that I've got ab squared all cubed. Well, I need to know that there's a 1 here, and I can multiply the 3 by both these things in the brackets. The result being a to the 3 times b to the 2 times 3, which is 6. We know the negative index law quite well, largely because of our work with the hyperbola and truncuses. However, we should also know that in methods we always look to keep our answer as a positive index. And that's why there's a little note down here about using the reciprocal law last. However, if I had something like a to the negative 5, b to the 6, all divided by a squared, we might think, well, a to the negative 5 can be brought to the bottom as a product of a squared, and we know this is b to the 6 over a to the 7. Also, we could have thought about doing this as negative 5 take away 2 is negative 7, and then bring it down to the bottom. The last law is just telling us what it means to raise to the power of a fraction. And so you can see all we need to do is take the denominator of that fraction. Yeah. So if we had something like 5 to the power of 2/3, we'd take that denominator. Yeah. And that now becomes the nth root, in this case the third root of 5 squared. So I think we know these quite well. However, looking at how they apply to log laws, we could actually use all of these laws to prove the logarithmic laws. We won't do that today, but if you like, we can do it in class a little bit later. Taking the first one, log xa plus log xb equals log ab. It's saying if we add logs that have the same base, in this case x, we know that we do the product of what's inside. And it should be noted here as a little bit of a typo. That should be log x ab. So for instance, if I had log 3 5 plus log 3 2, I actually have log 3 5 times 2, which is to say log 3 10. Now, a similar case here is if we subtract two logarithms of the same base. In this case, again, that base is x. We can divide what's inside. So the example here, log xa minus log xb, is log xa divided by b, which we can see there. If I take a very similar example that I just did, suppose I had log 3 2 minus log 3 4. I've got log 3 2 divided by 4, which is to say log 3 1/2. The third law here is saying that if I've got something inside the logarithm, in this case a, you can see it there, and I've raised it to the power of n, I can resolve that n by bringing it down to the side here. For instance, we might have log 3, 8. And I know that log 3, 8, well, the number 8 could be presented as 2 cubed. And I can take that 3, bring it down the bottom, and say that this is equal to 3 times log 3, 2. The third law here, where it says log x a equals 1, lets me know something about that a. If log x a equals 1, then I might say something like x to the power of 1 equals a. In other words, x to the 1 equals a. Now this belies, I suppose, what a logarithm really is. It simply makes the subject of an indicial equation the equator. So suppose I had on the side here a to the x equals b. Well, if we wanted to convert that as a logarithm, in our indicial equation, our base here is a, and that's not going to change. So you can see our base here is a, so I'll simply keep my base a. Now I'm saying the previous equator was b. Well, remember we said a logarithm makes the subject the equator, and vice versa. So that b is here. And finally, if we look at our old subject x, it is now the equator. So we read, or I read them anyways, as a to the power of x equals b, a to the power of x equals b. The very last log law is what we call the change of base rule, and really this is not one that's terribly common in methods. If you are doing physics though, you would have seen this quite frequently. So if I had log a x, as we have here, well, I can represent that expression as a base of anything. And the example here is log 10x over log 10a. So if I wanted to represent log ax as a base 10, I take what's inside the logarithm, which in this case was an x, and we put that as log 10x in the numerator. I take the old base, in this case a, and it becomes log 10a on the denominator. Now, using these to solve or simplify our expressions, if we have a look at our very first example here, we've got log 749 plus log 232 minus log 5 125. And the first thing that I should notice about all of these is that they all have a different base. So while I might be tempted to immediately start adding or subtracting logarithms, I need to first recognize that to use those two laws, we needed the same base, and in this case we don't have it. What I might recognize though is that 49 here is a power of 7. So we can try to rewrite this expression as log 7 squared plus log 2, now hopefully you've recognized at this point that 32 is also a power of 2. It's 2 to the 5. Minus log 5, now 125 is 5 cubed. Now put that one in brackets just to show you that it doesn't really matter how we write these. We should always read them as though they were in brackets. We can resolve these powers by taking the 2, bringing it down to the side here. So I've got 2 log 7 and I can bring this 5 down here. So I've got plus 5 log 2 of 2. And if I resolve the last 3, minus 3 log 5, of 5. Now one thing we might have recognised here is log 7 of 7 is actually equal to 1, because we have another law, and we might actually make that in green to make it a bit clearer, that log a of a equals 1, because a to the power of 1 is the only way we got ourselves. So that law again, log a of a is 1. So hopefully we've recognised that log 2 of 2 was 1 and log 5 of 5 was 1. And so this expression is really 2 plus 5 minus 3, which of course is equal to 4. And that's my answer there. Okay, next expression, slightly different. We've got x's involved, but we also can see that this is log base 4, base 4, base 4. So in this case we might look to express our answer, or rather to use the log laws of addition and subtraction. Before we can do that though, we'll have to resolve these coefficients. So this becomes log 4 x to the 7. This 9 will go minus log 4 x to the 9, and this 2 is plus log 4 x squared. Now we can add or subtract these. If I'm subtracting a logarithm, remember I'm dividing what's inside. So if we start with the first lot, log 4 x to the 7 divided by x to the 9 gives us x to the negative 2. And we've still got our plus log 4 x squared. So x to the 7 over x to the 9, remember we said that was log 4 x to the negative 2 plus log 4 x squared. Now x to the negative 2 times x squared gives us log 4 x to the 0, which in this case is 1. Now you might be looking at that and thinking, well, 4 to the power of what equals 1? Log 4 1, really log base anything of 1 is always equal to 0. If I had the power a and I had to raise it to something and the answer was 0, that something, the answer was 1 I mean to write, that something can only possibly be 0. So looking at this, log 4 1 equals 0. We can also use these laws. Remember, our learning intention for today was actually to solve equations. So using exactly the same principles that we've just done, we're now going to attempt to solve the expression. What I do need first to solve generally is everything of the same base. So here where I've got log 4 x minus 1 plus 2, I'm going to rewrite that as log 4 x minus 1 plus 2. I'm going to call this log 4 of 4. 2 times 1. So I haven't changed it at all, but I've represented that constant, that number 2, now as a log 4. And I'm saying minus log 4 x plus 4 equals 0. You might have noticed that I can resolve this up here and say that this is actually log 4 16. And if I'm adding these two logs, then we'll note we've got log 4 16 times x minus 1 minus log 4 x plus 4 equals 0. Now, if I'm subtracting logs, remember that we can always look to divide. So in this case, I've got the same base log 4, my numerator here, 16x minus 16, and on the bottom, I've now dealing with this subtraction of x plus 4, and that equals 0. Now I'm going to read this separately, and we might have to make a little bit of room here. But 4 to the power of 0 equals this fraction. We know 4 to the 0 is 1. So 4 to the 0 being 1. On the right hand side here I've got 16x minus 16 over x plus 4. If I multiply both sides by x plus 4, you might have realised we've now got 16x minus 16 equals x plus 4. If I think letters to the left, numbers to the right, subtract x and add 16. So subtract x, add 16, we get 15x equals 20, which of course means x is 4 over 3. And that's our equation solved. Looking at the next one, we can approach it in a similar way, or we can deal with the subtraction first, because both of these are log 3. So if we rewrite this as log 3 x minus 2 divided by 5 minus x equals 2, we're going to do a similar process to what we did previously, where we read it as 4 to the power of 0. So 4 to the power of 0 equals inside. 3 to the power of 2 is going to be what's on the inside here. So 3 squared equals what was on the inside, x minus 2 over 5 minus x. And if we multiply both sides by 5 minus x, we see they cancel, and I'll have x minus 2 equals 9 times 5 minus 9 times x. So 9 times 5 is 45. Minus 9x. Again, letters to the left, numbers to the right. We end up with 10x equals 47. And we know here we can leave it as a fraction, or we can leave it as a decimal, as 47 divided by 10 is exactly 4.7. We know we've got our answer there. This next skill is really not a very common one, as we mentioned, but we're being asked to rewrite the following expression. So in this case that's log 5, 9, and rewrite it as a base of 10. So really all we're asked to do here is change of base. So you may remember that we need a base 10 from the question. So this log 5, 9 is going to be log 10 something divided by log 10 something else. We'll take the 9 and put it up here, and then we'll take the 5 and put it here, and we're done. It's just one constant divided by another constant, and it has the exact same value as log 5, 9. Looking at the next question, we're now dealing with log 210. We want to express this as a base of 10. So again, we're going to say this is a log 10 over a log 10. We can take what was inside, this number 10, and the old base, put that on the denominator. We get log 10 10 over log 10 2, and of course we need to simplify that to 1. So my answer here is 1 over log 10 2. Now, as I mentioned, this is not a very common skill in methods. However, your ability to use this in order to solve some form of algebra problem, as we see in example 4, certainly does crop up every now and then. So, if I look at this worded problem, it starts off with a bit of context. It says that if p equals log 5x, and normally the word if there should be your indicator that it's going to give you some information that will help you solve the problem. If p equals log 5x, find, the thing that we're looking to find is log x 81 in terms of p. So we're not after the value of x here. We just want to represent log x 81 in terms of p, and p is log 5x. So knowing that p is a base 5 might indicate that we want to change log x 81 to also be a base 5. So log x 81, if we made that a base 5, you might see that the 81 goes on top, the x goes on the bottom, and we can see that log x 81 now has a p in it. And so we can rewrite this as saying log x 81 is log 5 81 divided by p, which is also the same as 1 on p times log 5 81.